So, well, because we are still considering a constant temperature reaction, so it's isothermal situation, we just need to connect the starting state, that is essentially a standard 1 atm state, to the final state, that is essentially a particular pressure that we are trying to look for. Then we just connect those two states through a reversible isothermal expansion, well, or compression, depending on the pressure, I guess, of the entropy. So we can construct that, and we learned actually from a previous lecture, this difference of entropy actually can be calculated as the heat transfer over temperature, that is a negative of the work over temperature, that is a negative nR times the log of the current pressure over the reference state pressure. So this is the result to say that based on this argument that the different pressure states will have a different entropy, and this entropy can be calculated as a log of the pressure times this constant. If we combine those two, that's to get into the definition of the G equals to the H minus Ts, then we find the difference between the actual G, the G's free energy under any given state, and the essentially the reference states of 1 atm, we just write it as that, the pressure of a given pressure in the reference state, is equal to the nRT log P over P reference state. Essentially, is to say, if essentially the H is not changing, it's 0 for delta, and in this case, there's a negative T, we just put it in there to reverse this sign and put an T over there. So just got that particular result. So this actually is very useful because now we can we know for any species that either is a product or a reactant, the difference of a given state of free energy when compared to the standard state is nRT log of this particular pressure over the reference state 1 atm pressure. So if we already figured out any species difference, then it's actually relatively straightforward to figure out what's the entire difference for the entire reaction, considering the entire equation of reaction. That is to say, we can write the delta G for this particular reaction into the delta G under the standard state plus the C times the delta G of this particular species plus D times the difference of the partial pressure of D of this species D minus the A times the delta G of A and B times the delta G of B between the reference state and the particular state you are looking at. So it's just math you can actually figure out this actually well holds true based on this type of equation. Essentially, this is to say we can decompose the delta G into two parts. The first part is the delta G of the reaction under the standard state in blue, and then the second part is essentially the difference of all the species at the specific pressures of that particular species when compared to the standard state. So that's actually the two parts. So now let's just put things in there, then we know that this, we just rewrite this thing, and in here we write C times RT log, essentially this thing, D times RT of this thing, and then negative of ART of those terms, so just rewriting that in there. And based on that, we can rearrange it, it's just mass of log, essentially. Whatever that you are adding outside the log, inside the log, you need to multiply those terms, essentially. This is mass. So if you put all those things together, you end up with the equation of the delta G under a given arrangement of pressure is equal to the delta G under the standard state plus LRT times the log of the PC over the reference state to the C, to this count of molecule, essentially moles, of PD over the P reference state to the D, divided PA over reference state A and PD over reference state to the power of B. So this actually is a formula that you might already seen before in an earlier chemistry class. Is defined actually as the reactant quotient to figure out what is the equilibrium, but we are going into the details of the definition right now. So this is to say, this thing looks a little bit complicated, but it's still pretty useful, and we want to define it as a particular thing. We just call this thing as Q in a sense. Well, in more details, Q is actually defined as A, which is the activity of a particular chemical species in the product and also in the reactant to the order of the moles in front of that particular equation. A, the activity, is the generalized term to tell you how active a particular component in a reaction is. And in that case, for ideal gas, the activity is actually just defined as the pressure over the reference state pressure, so it's unit length eventually. So if the reference state is 1 atm, then the PA over 1 atm, the partial pressure of that particular species over 1 atm is activity, it's a unit length thing. But at the same time, it's also generic, meaning that it applies to ideal gases, but it also applies to solutions, for example. And in that case, the activity of a particular species is approximately the concentration of that species over the reference state of a solution. The reference state typically is defined as 1 mole, so 1 mole per milliliter per liter, essentially 1 m. So that is for the ideal solution. We will go into those concepts of ideal and non-ideal solution later in our class, but for now we just say if it's an ideal system, then just divide your concentration by 1 mole per liter, and that is activity that you can plug into the reactivity quotient. So this is essentially, for those two cases, we actually previously mentioned the partial pressure of a gas system is essentially defining the concentration of the gas anyway. And at the same time, in a similar analogy, then the ideal solution concentration is also a definition of activity, similar to the case in here that PA partial pressure is immediately linked to the concentration. So those are both essentially telling us if a substance is higher in concentration in a given system, it has more stronger reactivity in a sense that roughly speaking is holds true anyways. If you think about it, if you have more of this particular thing per volume, you actually have a better chance for the reaction to occur, essentially push the reaction towards a particular direction. But what you also need to note in here is that pure solids and liquids never enter into the reaction quotient, like the type of Q. Actually, they always are, by definition, a number of 1 is always assumed for pure solids and liquids. The reason for that is that we consider a pure solid system or a pure liquid system as only one particular arrangement. There are no changes in entropy if you try to change the amount of those things in your system. It's always the same solids that give you the same number. Another way of thinking about it is a little bit abstract, but it's also the reaction for solid and liquids. Typically, they can only interact with things on the surface anyway. It doesn't matter how much you have inside. And the reaction actually are always defined by how they actually are interacting with the other place as opposed to whatever entire number that you have in the system. But just to emphasize again is to say the pure solid and liquid does not change entropy no matter how much you have in your system, so they never come into the reaction quotient. So this thing is useful because, as we say, this is essentially linking the delta G for a given particular system to whatever other ratio of the different things actually in your system. And this actually is directly related to the concept of equilibrium. That is to say, again, this is the same reaction of A plus B to the C plus D. That we now know that by the definition in here is to say the delta G at a given state is equal to the delta G under the standard state plus RT log this Q, this quotient of the ratios of the product and the reactant. This is the equation again, and this is the definition of Q again. But this actually gives us a way to establish equilibrium as opposed to one single direction of reaction, but actually both way of direction. We say we define the equilibrium as a situation where the delta G is equals to 0. So we mentioned this before, that if the Gibbs free energy is 0, it essentially means the system has no drive for the reaction to go either towards the product or the other reactants. It actually is under equilibrium, meaning that you do not see macroscopic change over time. It's actually stabilized. So if you consider equilibrium, then we are saying if we want to find out what's the Q in EQ, meaning the reaction quotient under the equilibrium situation, then we essentially need to say if the delta G is 0, if the 0 is this term, what will be this particular term? Essentially just putting 0 into this particular definition, well, relationship of delta G and Q. then we say 0 equal to the delta G under the standard state plus RT log Q under the equilibrium state. And this can be just rewritten as delta G under the standard state is equal to the negative of RT times the log of the Q under the equilibrium state. And this particular Q, which is a well-defined number for a given reaction system under constant temperature, is called the equilibrium constant K. So essentially we define the Q under the equilibrium situation as the equilibrium constant K, and if that's the case, then we say the standard state delta G is equal to the negative of RT times the log K of this particular constant. So again, the K is a constant, meaning that it does not depend on how much the reaction has progressed. What is the actual concentrations of the different species in a system is a given constant for a given reaction. Is exactly because the delta G under the constant state is a given constant. So this thing never change for any written reaction, and because of that, at a fixed temperature, the K will not change for a given situation. The K will be the same. On the other hand, the Q will change as a function of reaction, because by definition, Q is just essentially the amount of products over the amount of reactant in your reaction. So Q will change over reaction. So what really happens is that at equilibrium, by definition, the Q is equals to K, because K is essentially defined as the Q under equilibrium. So this is just restating the same thing. However, when the reaction is away from equilibrium, meaning that the reaction quotient, meaning that the ratio between the product and the reactant is not exactly a number of K. Essentially, if the Q is not equals to K, then we can write the delta G in this case by considering those equations to say the delta G is equal to the delta G under the standard state plus RT times the log of the actual Q for that particular state. So this is essentially writing this particular formula. But now, because the delta G under the standard state is equal to the negative of RT of the log K, we just rewrite that in there and just math again that it's equal to the RT of the log of Q over K. So this equation, although not in a box, but it's actually still pretty important because it immediately tells you what will happen for a particular reaction that has a Q being smaller than K or larger than K. For the first case, that if the Q is smaller than K, this is essentially to say we do not have enough products, because remember, the Q is defined like the product of the reaction over the reactant, essentially. So a Q being smaller than a number than the K is to say the system do not have enough product,